Welcome everyone. We're just going to wait a few minutes to make sure everyone else who wants to join is able to join. Okay, great. Thank you, everyone. We have so many people here joining us live. I'll start by introducing myself. My name is Chris. I am going to be the lead TA for this today's lecture on AI for power and energy systems. And so let's just get started. So Climate Change AI, hopefully, as you all know, is a global nonprofit working on catalyzing impactful work at the intersection of climate change and machine learning. As summer school students, you already have probably seen the website, joined the community platform, hopefully signed up for the newsletter. So just a few housekeeping items. Please use the chat for general comments and ask questions using the Q&A feature on Zoom. We will be looking through these questions throughout the lecture and asking them to the speakers. As unfortunately we won't be able to necessarily answer all questions, but we'll do our best to do that. And so really excited today to be introducing two amazing speakers, Professor Priya Donti and Dr. Simone Nsutezo Fobi. So, so Professor Priya Donti is a professor at MIT. She is a co-founder and chair of Climate Change AI. Received her PhD in computer science and public policy from Carnegie Mellon University, and as the recipient of the MIT Technology Review's 2021 35 Innovators Under 35 Award. And Dr. Simone Nsutezo Fobi is an applied research scientist in the Microsoft AI for Good Research Lab. She did her PhD at Columbia University and also holds a master's degree from Stanford University, and also worked as a research scientist at the IBM Research Africa Lab in Nairobi. The more detailed parts of their bios you can read on the screen and find online. And with that, we'll switch it over to our speakers today.
Thank you, Chris, for this warm introduction, and we'll get started here if it's okay. Can everyone see my screen okay? Perfect. Hello, everyone, and thanks for joining us for this lecture on power and energy systems. It's my pleasure to be co-lecturing today with Priya, and I'll give her a minute to say hi before we jump into it.
Yeah, hey everyone, super excited to be here with you today. And just because it didn't get said at the front, thanks also to Chris and Ruth, our awesome TAs for today.
Yeah. So we'll get started with the lecture. I'm sure everyone is well aware we'll be focused on power and energy systems today. And the goal for this lecture is a few things. One, we want to be able to contextualize what climate change mitigation and adaptation means for the power and energy systems sector, and be able to call out why sustainable development strategies are also as important for this sector when we think about climate-related strategies. To do that, though, we need to present background on how electric power systems work and share with you guys either what are the opportunities or what are some things to keep in mind when applying ML to the power and energy systems sector. We will then go into some detailed case studies to look at how ML was used and how we should be framing ML-related questions for true impact in this space. And finally, we want to share from our personal experiences what some potential entry points or next steps might be for you, and also hear from you on how you will take this moving forward. So with that in mind, we'll start off with why should we care about climate change in the power and energy systems sector? When we look at emissions as reported by the IPCC 2022 report, the numbers that we see is that the energy supply sector contributes about 1/3 of CO2 emissions as compared to other sectors. Now, depending on how we do the accounting, meaning that if we look at, say, the building sector and the energy used in building materials, that accounting might shift these proportions a little bit. But the general idea here is that the energy supply sector is a huge contributor to the emissions that we see. And what do I mean by energy supply sector? This refers to any infrastructure or any equipment that is used to either extract, transport, transmit, convert energy so that energy-related services can be provided. This can be related to what we're familiar with, which would be electric power systems, but it can also account for fuel systems, either natural gas, cooking fuels, or even heating and cooling systems that we may be familiar with. So now we know that this sector is a huge contributor, and maybe there are opportunities for us to implement a few things that can help mitigate climate change impacts for the sector. Another thing to keep in mind here is when we look at low carbon sources in the space, and we would see that for the electricity sector, low carbon sources account for about 1/3, almost 40% of energy sources. Whereas when we look at the total energy sector, low carbon sources are actually still in the minority. So we still have a huge proportion of energy related services that are not from low carbon sources. And again, this is an indication that there might be an opportunity for us to consider what some opportunities are to increase this proportion. Before we move on though, it is important for us to call out that low carbon sources are not equivalent to renewable sources. Yes, there's overlap, but there's a clear distinction between both of them. And in this particular case, these figures are highlighting at least the combination of low and renewable energy. So again, coming back to my initial question, why should we care about climate change in the power and energy systems sector? First things that we observe is that there's an increasing pressure on power and energy systems as a result of climate change. What that means specifically is that one, we are seeing an increasing number of climate-related events. This can also mean increasing the intensity and the variability of those events, where we're experiencing a lot of more heat spells, cold spells, and this can also lead to a change in the demand pattern. So for example, in the Pacific Northwest, where I live, we're experiencing this summer, we had very, very hot temperatures. And again, this relates to these 2 points of one, variability in climate-related events, but then this also shifts the demand for heating and cooling in the Pacific Northwest, where we didn't previously have heating and cooling built into our homes. The second reason is that the power energy system sector is transitioning, is shifting. And what I mean specifically is that we're shifting from the traditional, if I may say, higher carbon sources to low carbon sources. And what that means is that these carbon sources, say in the case of renewable sources, might be weather dependent. And with changes in our climate, this can actually directly impact the amount of energy that can be produced and by consequence supplied to consumers. Again, in regions that are also incorporating more, say, renewable or low carbon sources, we're expanding our infrastructure, either reinforcing our existing transmission system or due to growing global population, increasing access to regions that previously didn't have electricity. So with this increase in the infrastructure or the grid infrastructure or power infrastructure, we are more susceptible to climate-related events. So we need to actually think about how do we make the grid as a whole, or how we provide power and energy as a whole, more, let's say, robust and resilient to climate risks. The other point that's not necessarily brought out in the previous slide is that we've seen that income and economic growth moves in lockstep with electricity consumption. This figure here shows, if you look at Vietnam in the 90s or South Korea in the 90s, and how they've been able to grow their per capita income with time, this has also moved in lockstep with how much electricity has been consumed in these economies. So what this might suggest is that income growth is directly tied to electricity usage. And while we are enforcing or pushing for strategies that mitigate climate risk in the power and energy sector, we need to make sure that we do it in such a way that we're not prohibiting economies from growing, we're not prohibiting people from gaining income and being able to live decent lives. So what that might mean in terms of climate adaptation and mitigation strategies for emerging economies versus maybe developed economies, the implementation might be different. Let's say for industrial economies, we would have to maybe focus more on reducing emissions while maintaining the levels of development that have already been achieved, the progress that has already been made. But for emerging economies, while we're either maintaining or reducing emissions, we still need to push for an increase in the development levels that are seen in those economies. So now that hopefully I've been able to convince you why we should care about it, Priya, I think, will hop in and talk a bit more about mitigation and adaptation.
Absolutely. And so I think Simone gave a really nice overview of why energy systems are so important for mitigation, adaptation, and sustainable development. And so we're going to use this time now to talk through how we actually make progress on these objectives. How do we decarbonize energy systems? How do we make them resilient and robust to climate change? But before we tell you, we actually are curious to hear what your thoughts are. So I'm going to give everyone a minute or two to maybe submit in the Zoom chat and your thoughts or answers to this question on the slide, which is, what are some strategies to decarbonize energy systems?
I see in the Q&A there's a question about what's a good source for energy consumption on the country and sub-country level. I assume that's referring to data sources for that. Either Priya or Simone, do you have maybe some suggestions for data sources on that?
Priya, if I may briefly answer, we do provide a few resources for data at the end of this lecture, while it might not necessarily be specific to that question, but at least maybe that might be a starting point. We do provide some resources at the end of the lecture.
Yeah. And I'm not 100% certain, but my first guesses would be the International Energy Agency or Our World in Data as potentially two sources that might have it, but I'm not 100% sure. Awesome. So thanks for all the answers coming in the chat. So I see various categories of actions here that make a lot of sense. So one of them is thinking through kind of how we actually supply power, right? Make it more renewable, stop using fossil fuels, and so forth. Another has to do with actually the efficiency of how we actually provide various sources of power. And then another has to do with, let's see, actually, changing how much we consume and how we consume via demand response and such. And so these are really great. These are hitting the nail on the head. And what we want to do in the next few slides is provide a little bit of a framework to actually kind of conceptualize the different ways that you can actually decarbonize energy systems. So Simone, if you'd mind going to the next slide. So the basic idea is that when we think about decarbonizing energy systems, the approach in different countries and different contexts will depend on the specific national circumstances, but there are some commonalities in approach that are shared between contexts. So next point. And a particular conceptual framework that we can use in energy-related sectors is called the CCAI identity. And this breaks down greenhouse gas emissions basically into the multiplication of a few different terms that each indicate strategies that we actually have to reduce greenhouse gas emissions. And if you go to the next point, one nice thing about this identity is it actually connects things that you can do on the supply side as you're actually providing power and providing energy to places, and on the demand side. So what you can do with respect to, for example, transportation, buildings, industry, and other sectors that consume energy. And so we're going to walk through this particular CCAI identity term by term. Next. Okay, so the first term in the CCAI identity that we're going to break down is this term service per population. If you could go next. What this refers to is the idea that when we're consuming energy, we're not just doing it to consume energy, right? We're trying to actually get something or do something. And the question is how much of that thing, how much of that service we consume per person, reducing consumption is one lever that we have to actually reduce greenhouse gas emissions. So to make that more concrete, next point, we're going to use the example of passenger vehicles. So trying to connect some things you might have heard in the transportation lecture to things that you're going to hear in this lecture. In this case, in the case of passenger cars, the service that we might be talking about is the number of vehicle kilometers traveled. So how far you actually get to travel in a vehicle. In this context, next, what reducing consumption might mean is reducing the number of kilometers that are actually driven. For instance, I as an individual could move closer to work so that I don't have to drive as many miles or kilometers to work every day. And there are systemic changes that can also be made, actually changing, for example, how we build our cities to actually allow people in general to kind of live closer to where they work so that the kind of total need for the number of kilometers to drive goes down. You can also increase the number of passengers per trip and per vehicle. So even if you keep the number of vehicle kilometers driven by a particular car the same, if you divide one car trip by one person versus by two people, you can also reduce this term of service per population. And the kind of general strategies that these imply, one is that you can do kind of individual behavior changes, but also, and importantly, that systemic changes and structural improvements can really change how much we consume per capita. So going on to the next term in the CCAI identity, this is the term energy per service. So imagine that we've decided we do want to travel a certain number of vehicle kilometers. How can we actually reduce the amount of energy that it takes for me to get that? Again, remember, in some sense, as a person, I don't care about energy, I care about service. So if I can get the same service for less energy, that's improving efficiency, and that's pretty great. So in the context of passenger cars, if we go to the next point, there are a few things that can be done here. So one is improving vehicle efficiency. So you hear about, for example, kilometers per liter or miles per gallon fuel efficiency of cars. You can actually improve that via kind of technological change. You can actually drive more efficiently in ways that improve the number of kilometers you're getting per unit of fuel. And you can also switch to other modes of transportation, things like bikes, which are much less energy intensive per distance traveled than passenger cars. In general, what this kind of leads to is a combination of efficient end-use technologies, so the technologies that are actually providing this service, like the car, making those more efficient, but also more efficient generation technologies. So if I can actually, for instance, when I'm transporting power to your electric vehicle, actually reduce the amount of power that's lost along the electrical lines, that's also a way to kind of improve the efficiency here. And so the last term in the CCAI identity is greenhouse gas emissions per energy. And this is one that I think a lot of your answers in the chat got at, which is that to provide a certain amount of energy, we have a choice as to which energy source it comes from. Does it come from fossil fuels or natural gas? Does it come from renewables? And basically this lever is by switching to clean energy, we can reduce the greenhouse gas emissions that are associated with each unit of energy that is used. And so in the context of passenger cars, this can involve strategies like switching to battery electric vehicles that are powered by a clean power grid. And of course, that's very important. You need to green the grid alongside switching to battery electric vehicles for this to work. Or another option is to switch to alternative liquid fuels like electrofuels, solar fuels, or hydrogen fuels that are produced in a lower carbon manner and that emit fewer emissions when actually burned. And the general strategies implied by this are a combination of electrifying and switching to lower carbon power. So move to electricity and make the electricity cleaner, as well as replacing fossil fuels with clean alternative fuels. And kind of, this is, in some sense, a summary, a conceptual summary of things that you can think about doing in energy-related sectors. Again, reducing consumption, improving efficiency, and switching to clean energy. But in looking at each individual component, we also shouldn't lose track of the larger picture, which is ways we can drive reductions in greenhouse gas emissions directly. And so going to the next point, we also have access to economy-wide strategies to reduce total greenhouse gas emissions. And that involves things like targets, regulations, standards, and investments across the economy. Strategies like carbon pricing, which directly try to cap or to tax the amount of greenhouse gas emissions that a particular entity might produce, and then they might take some of the levers implied by the right side of the equation to try to actually make that happen. And of course, some carbon dioxide removal as well.
So far, Priya has been able to call out how we can decarbonize. But if we can take a minute to, having considered decarbonization, how can we adapt power energy systems to climate change? And please feel free to drop your thoughts in the chat. Maybe we can take a minute or so to do that. What would be some strategies to adapt our current systems to climate change? Okay.
And while folks are dropping questions in the chat, so there's a really great question from an attendee about, the CCAI identity has a population term. And so this is basically using a mean value for each person. And of course, different people around the world consume different amounts. So the way I would take the CCAI identity is, so in some sense, if you were to use it to actually compute greenhouse gas emissions, you would have to use averages across the terms across the world. I think of it more as a conceptual identity, which is to understand in any given context, what are the different kinds of things you can do. And of course, as are also emphasized in the kind of intro on sustainable development, the strategies in different places will need to differ significantly. People in developed contexts consume much more than those in developing contexts. And as a result, we shouldn't, for example, treat the reduced consumption term equally across all contexts. So that's a great question. And I would think of it more as a conceptual way to break down the strategies rather than something that we use to literally calculate the greenhouse gas emissions in reality.
Thanks for that addition to Priya. I see that the chat is quite buoyant, but a few things that stand out to me here are around grid modernization. I also see some points around improving resilience or increasing resilience in infrastructure and assets. I see some comments around better forecasting, all of which are touching on very important strategies for adaptation. So starting off with the first one that I want to call out is increasing robustness and resilience. And for those that made this point, maybe they were reading our minds a little bit, but yes, this is a huge point. And the difference here is that robustness here is the ability for the grid to handle events, while resilience would be the ability for the grid to regain operation after such an event. So here, for example, when we say being able to be robust means accommodating correlated failures. This can be in the case of extreme weather events. How well are we able to handle such situations? And resilience here would be, can we quickly repair the infrastructure that is down and come back after such events? In reality, I think both of them play well with each other, where we have this somewhat cyclical process where we prepare and build robustness into the grid such that during the event we can handle it as best as possible, and then enabling quick recovery and learning from those observations so that we can be better prepared against the next event. Another way too is accommodating changes in supply and demand. Yes, we do anticipate that changes in weather will impact energy production or impact consumption, but are we able to better handle those changes in demand that might occur due to extreme heating, and do so with low carbon sources? The third point here is around building adaptive capacity. And what we mean is that while we increase access and reliability, as we've seen, these are strong drivers for economic development and can empower people to be able to better respond or better adapt to changes in climate. So while we push for solutions or approaches that directly impact the grid, also ensuring that we provide energy or electricity at levels that people can actually use to gain economic independence is also as important. Having provided that context, I'll hand over to Priya.
Yeah, so far we've talked about in some sense, macro level strategies to really think about how you decarbonize an energy system or how you adapt it to climate change. But in order to really truly understand the nitty-gritty of these strategies, we actually want to do a little bit of deep dive into specifically how electric power systems, again, remember, one type of energy system, but an important one, how electric power systems actually work. And so if we go to the next slide, we're going to, you'll notice a bit of a pattern. So we're going to ask you about things before we actually tell you about them. So the question here, if you could answer it in the chat, is what is an electric power system?
As people start typing answers in the chat, I think this would be an appropriate time to bring up a question from the Q&A, which comes from Ali Mashoud. How can we integrate smart grids with complicated energy systems in third world countries?
Yeah, this is a great question, and I can take a little bit of a stab, and then Simone, if you also have some thoughts. In some ways, actually, it can sometimes be harder to integrate smart grid technologies into developed country infrastructure than in developing countries, depending on whether you're thinking about retrofitting existing systems versus building out new ones. So, for instance, if you are kind of creating a new energy management system or creating a new microgrid, you have the ability to integrate sort of the latest and greatest technologies in terms of the software systems that are used to manage power grids, as well as the sensing technologies, in a way that retrofitting doesn't necessarily allow. Now, technology costs can be more expensive with some of these installations, and that can create a lot of inequities. And so equitable financing and finance transfers become a really important part of this. So from a financial perspective, there's a lot that needs to be done to basically redistribute financing to enable this. But from a technical perspective, actually, in some ways, outfitting new or newer infrastructure with smart technologies can actually even sometimes be easier than retrofitting existing technologies.
I do echo Priya's perspective. I think the other thing we want to keep in mind is what are some of the questions or challenges that we want to be able to solve when implementing smart grid technologies in emerging economies. I think that can also really influence the design of such systems with the goal of easier integration, but also reducing the cost for such devices. So I think I would try to approach it in a more holistic way, in a sense that if we could know priori what we want to be able to answer with such technologies, then we can design technologies that better suit the environment, rather than, say, picking up technologies that have already been pre-designed and might not necessarily be suited for the context.
Simone, there also look to be 2 questions in the chat about climate change adaptation and disaster risk management. I don't know if it makes sense to take them now before we move on to this next section.
Sure, if you don't mind calling out the question.
Or not in the chat, sorry, in the Q&A. So one of them is, how much can forewarning actually mitigate the impact of disasters? And the other one is, extreme weather causes lots of disruptions. Do these strategies take into consideration the history of predictive models of extreme weather patterns across the globe? Oh, and you're muted.
Okay. Yeah, I think with the first, at least the first one I see is around extreme weather causing a lot of disruptions. Does this take into account predictive models? I think we do need better predictive models for weather, and also tying into what the impacts are going to be either on generation. And I think we do have a case study actually that talks a little bit about that. How do we move from weather models to what that might mean for planning in power systems? So yes, that is a strategy and should be taken into account. What we may not have necessarily discussed are how to frame that question, understanding where the boundaries might be and how we actually use it for impact within the space. The next question is, how much can forewarning actually mitigate impact of disasters?
So I have some thoughts on that.
Yeah, you can go ahead, Priya. Yeah.
It depends on the nature of the disaster, and it depends on the amount of forewarning. So for example, if you have a sense that more likely certain parts of the infrastructure over the next 10 years, then you can actually build up and retrofit your infrastructure to be more resilient to the impact of hurricanes by reinforcing certain lines, for example, in order to then make sure that that part of the system is stronger. When it comes to nearer term warnings, there are again some cases where forewarning can help. Not a climate change related example, but in India, during the COVID-19 pandemic, there was a moment in time when the government said, hey, can everyone shut off their lights at this specific time of the day and sort of step outside and clap to give thanks to all the healthcare workers who are working very hard in the context of the COVID-19 pandemic. And that action caused or could have caused a very sudden dip in electricity consumption. And if a power grid operator has to look at that and see that in real time and scramble in real time to figure out what to do, that's very different than if they have a little bit of warning ahead of time to tell different power generators, hey, you actually should probably ramp down or shut off or start to shut off your power because we will have a dip in generation at this particular point in time. So there are strategies you can take both on planning horizons and in real-time operations horizons based on warning. Not everything can be fixed with a warning, but some things definitely can. Awesome. So I'm going to move us on to this particular section. So thanks to everybody who contributed into the chat about what an electric power system is. And I think a lot of you have some very great ingredients in there. So I'm just going to move on to the next slide and kind of spell out our conception. So when we talk about electric power systems, we're talking about the systems through which first click our electricity is produced. And then if you don't mind clicking, Simone, and that's our electricity generation infrastructure. That electricity generation is then transported along lines and electrical equipment to where it's consumed by end-use consumers like us. And in the middle there, this transmission and distribution portion, transmission refers to the part of the electrical system that is transporting power at very high voltages, very long distances. And distribution refers to the part of the grid that is transporting power shorter distances at lower voltage. An analogy to think about why this is the case is to think about road transportation, where often we have a combination of highways and service roads. You take a highway in order to go a very long distance very quickly, but if we always went that speed near where we lived, a lot of people would get hit. So we don't want to do that. And so nearer to the final destination where we want to go, we exit from highways onto service roads, which are roads where we go more slowly, in some ways less efficiently, in order to get that last mile or last few miles to our final destination in a way that's a bit safer. And so transmission and distribution are similar. High voltage is less safe, but is much more efficient for transporting power. And so our transmission systems take that take power that large distance very efficiently. Distribution systems take it that last stage a little less efficiently. And while that last slide presents in some sense a one-way idea of how power systems work, from power flowing from generation to consumption, electric power systems are rapidly changing in various ways. So first, we're starting to see bidirectional power flows, which means that we don't just have big power generators sending power towards consumers. We also have things like rooftop solar panels on homes or batteries that are connected to the distribution system that are actually shooting power up the other direction. And so we're starting to see a power grid that's operating not in a one-directional power flow, but using bidirectional power flows. We're also seeing, whereas before power grids were often operated in a centralized way, where we had power grid operators or a market dictating how large power generators would actually produce power, we're starting to move to a lot of non-centralized control paradigms. So for example, before electricity demand was viewed as inflexible, it's a given, the power grid has to deal with it. Now we're seeing strategies like demand response, where electricity consumers can actually change when exactly they're using power based on the needs of the grid. And that is in some sense a form of decentralized or distributed control. And there are actually two different paradigms for non-centralized control. Distributed control basically says we have many different devices that are trying to mirror what would happen centrally. So maybe we tell them what to do, but we tell them what to do. We give them some information to act in a way that's coordinated. Decentralized control basically says all of the devices kind of independently decide what they want to do. And we might send things like prices through a power market to incentivize them to have certain behavior, but ultimately each device is going to decide independently and based on its own kind of self-interest what to do. So there's some different paradigms there. And then we also have a distinction between on versus off-grid setups. So for example, in islands or in rural areas that are very far away from a centralized power grid, it doesn't always make sense to try to kind of put connections from a big centralized power grid to a farther away place, because it can lead to certain inefficiencies and as you transport power very far distances. So for instance, some places might have off-grid microgrids, which are smaller power grids that are independent in certain cases, or there might be smaller grids that are semi-connected to a larger grid. And also in some cases, homes might have personal power sources like a solar panel and a battery. And then last but not least, given that we're in the climate change AI summer school, many people may also have on their minds the impact that AI and data infrastructure are also having on electric power systems. In particular, we're seeing, due to kind of recent advancements in and increases in use of generative AI technologies, that there's been a lot of build outs of data centers and infrastructure in places where this wasn't previously anticipated. And that's led to things like extensions of the lifetime of coal plants that were slated to retire. Now, this is a situation where planning is helpful, right? If you know how your electricity load might change due to AI or due to other factors, you can kind of plan to service that using renewable energy. We also should make AI more efficient. But in the near term, at the very least, this is having an impact because in some sense, electric utilities aren't prepared to deal with the growth associated with this. And so this is something we should keep in mind as well. So when thinking about kind of how a power grid works, it's important to understand that power grids are physical systems. And so there are various kinds of physics and constraints associated with power grids that need to be satisfied at every single moment that you're operating a power grid. So, for example, at a high level, there always has to be an exact balance between the amount of power that is produced and put into the power grid and the amount of power that is consumed. And so at every single moment in time, you have to maintain this exact balance between power input and power consumption. Now we can kind of go even a step further and write down kind of a set of mathematical equations that characterize, in some sense, the key goals we have when actually operating a power grid. And we're going to use an optimization problem called AC optimal power flow as our way of kind of showing, in some sense, what it would look like to ideally operate a power grid. So the idea is that in an AC optimal power flow style setup, we have a power grid operator that's going to tell all of the different controllable power generators on the grid what their power and voltage set points should be. And the goal is to do this in order to, next bullet, meet power consumption. So again, kind of power production and power consumption need to match. And when we say power consumption, that means a combination of true power consumption. So for example, the load coming from, lighting and heating and cooling and such, minus the power that's lost along the lines as it's transported. And also accounting for example, rooftop solar, which we often think of if you're a centralized power grid operator. Rooftop solar production is often thought of as negative consumption from the perspective of the centralized operator. In addition, you want to try to minimize costs, so minimize the cost of providing power. And you also want to satisfy various constraints associated with how power flows along the electrical grid and how much you can change power consumption. So this is characterized by, again, an optimization problem called AC optimal power flow, which is on the slide. And so the kind of terms in this optimization problem have to do with, the first term is the objective, which is minimizing the cost of power generation. The next term has to do with various equality constraints, which I'm going to skip over. The third term has to do with the fact that power generators have limits in terms of the minimum and maximum amount of power they can produce. And also lines have limits in terms of how much power they can actually transport. So we have bounds on these quantities codified within our problem. And then the last term is our power flow constraint, which basically dictates that the amount of power flowing into any node on the power grid has to equal the amount of power flowing out of the node on the power grid. And this ends up being a function of power generation, power demand, voltages, and the resistances or admittances of the lines. And then for those who are familiar with optimization and the concept of duality, which I realize is not everybody, so don't worry about that. But for those who are curious, the dual variables on this last equation actually are the prices of power on the power grid. So there's a relationship between this optimization problem and what you would see in a power market. So that provides, in some sense, an idealized representation of how power grids work. But in reality, power grids are, more complicated. And so I'm going to give maybe a minute to folks to maybe drop some thoughts in the poll. What are some ways in which operating a power grid might actually be more complicated than what we just showed.
In the meantime, there's a great question in the Q&A from Matthias. Are there any data sets or collections that would be recommended for someone jumping into energy forecasting, be it grid graphs, asset specification, generation or consumption, etc.?
Yeah, so some data sets that exist are, for example, in the US context, the major independent system operators or regional transmission operators like PJM, CAISO, et cetera, will publish aggregated information about electricity supply and demand. When it comes to asset specifications in the US context, there is some information from the Environmental Protection Agency that tells you the amount of power generation at an hourly level from any fossil fueled units above, I think, 25 megawatts. So you can get some granular data there. Grid structure specifications tend to be very protected because of safety or market reasons. So even in the US, which I'd say has some of the more open grid data in the world, grid topologies and grid asset specifications tend to be hidden. And so we tend to have to use synthetic test cases provided by entities like IEEE. I'm not as familiar, unfortunately, with the data landscape in other places around the world, but it unfortunately, I think, is not even as open as that elsewhere.
Thanks, Priya.
All right, so thanks for the answers in the chat. So there are lots of really great answers in there that I'm not going to get to kind of summarize or read through all of, but just if we go to the next slide, I'm going to throw up a bunch of text and basically indicate a few ways in which reality might be more complicated, many of which are captured in the chat. So one of them is that the optimization problem I showed, AC optimal power flow, is actually kind of expensive to solve. It's a non-convex problem with nonlinear constraints. And so power grid operators use approximations in practice. We showed what happens when you schedule power at one point in time, but you actually have to schedule power over multiple points in time. So you have to decide which power generators to turn on and off, and also how much you're going to change that power generation from one moment to the next. Many quantities on power grids are uncertain, so you don't have a perfect picture ahead of time of electricity demand or electricity generation. And so you both have to make those predictions and also make real-time adjustments based on what actually happens on the system. And there are all sorts of, outages, more nuanced physics that happen on the power grid, as well as some nuances with respect to power pricing. The location, the prices, the dual variables on the power flow constraint that I showed before, those are in some sense wholesale prices. But for example, consumers face retail prices. Some power generators are compensated outside of the market to incentivize them to keep running and provide kind of capacity to the grid in the case of extreme events. And there's a lot of power that's not actually procured through markets. A lot of power, more than 90%, is procured through power purchase agreements, which might be bilateral agreements between a generator and a large consumer. So while hopefully the idealized picture provides a little bit of a mental model as to how grids work, of course, when diving into this topic, it's important to understand the ways in which those models might be slightly incorrect or slightly limited. So I think one of the last things I want to talk about before I hand it over to Simone is, while we've talked about power grids as a technical system, in reality, they're a socio-political technical system, which is to say there are lots of entities and lots of policies that actually govern how power grids work. So first of all, power grids are quote unquote natural monopolies, because power grid infrastructure tends to be, in some sense, it's hard to build two sets of power grid infrastructure in one place. There tends to be one set of power grid infrastructure, one entity or set of entities that manages it. And as a result, these create natural monopolies where it's not kind of that many competitive entities can come in to manage the system. And as a result, these grids tend to be managed either by public entities or by private entities, but entities that have really, really tight regulation on them. In addition, there are lots of different stakeholders that come into play. Regulatory commissions that are setting high-level requirements and parameters, system operators who are responsible for maintaining low cost and reliability, utilities who might actually own or manage the actual physical equipment, suppliers, demand aggregators who are working with multiple consumers to help aggregate and make their demand more flexible, and consumers and others who are participating in the market. So again, understanding the stakeholder landscape becomes quite important. And then some other considerations to keep in mind. One is that different power grids in different parts of the world have different assumptions. If you could click to the next bullet, on whether consumers get 24/7 reliable power. So in, for example, the US, there is an assumption that whenever I flip on my switch, I should be able to turn my light on. Whereas, for example, in some parts of India, there are scheduled and regular power outages that are communicated potentially ahead of time and potentially not, but there isn't necessarily always that same assumption that power is always available. In addition, power utilities and system operators are incentivized financially in different ways around the world to take or not take actions to modernize the grid. So for example, many entities the way they make money is through something called a regulated rate of return, which is for every dollar or unit of currency that they spend on a physical grid infrastructure improvement, they get some kind of rate or percentage back. But in general, around the world, this tends to apply to physical improvements like putting infrastructure in the ground. It doesn't tend to apply to software related improvements. And so actually financially, there often is not an incentive among power grid operators to modernize their infrastructure from a pure financial perspective. Although, of course, as grids get more complicated, there's an implicit incentive that a lot of this more fancy software is needed to deal with that. So with that, we've kind of spent most of this time giving an overview of, power systems and energy systems in general. And I'm now gonna kind of flip over, and I forgot, I guess not handing it over, I'm continuing on, but we're gonna flip over to doing an overview of where machine learning actually plays a role here. So we're going to give a really quick overview of various categories where machine learning plays a role across operations, planning, innovation, policy and markets, and data management. So first, diving into power grid operations. And we can go to the next. So one category of ways that machine learning plays a role in power grids is by helping us to actually understand and assess the state of the power system as it stands. So this might be the current state of the system. So based on data I bring in, what are the voltages? What is the structure of my power grid? I might actually not know this. Or are there any outages on the power grid? And we also might predict something about the future state. So prediction of future renewable energy supply, demand, emissions, and so forth. And where machine learning can play a role is in actually helping to estimate these quantities, where the kind of pro of machine learning against other methods is that it's fast. It can use many different types of data, sensor data, image data, and learn correlations between them. And as a result, it's actually been a really powerful tool for near-term and real-time predictions. The challenge, though, is that machine learning methods tend to require consistent data, so that I have similar data coming from my sensors at every point in time. And in situations where sensors are noisy, where there might be missing measurements, that's sometimes difficult. And sometimes machine learning methods also struggle with longer term trends because they are learning relationships in present data that may not always generalize to future data. So in those cases, rule-based systems, physics-based systems, optimization statistics can play an important role as well. In terms of a specific case study, one example is the example of electricity nowcasting. So for example, the nonprofit Open Climate Fix worked with the UK power grid operator National Grid ESO to improve their electricity supply and demand forecasts by a few times in terms of reduction of error. And they did this through a combination of more advanced deep learning architectures, as well as by cleverly combining multiple sources of data, like time series data, satellite data, and the predictions from physical weather models. So, okay, so we know the state of the system. Now, how do we actually manage the power grid? So one kind of strategy we have is to actually better handle how we actually schedule controllable power generation in a centralized power grid. So recall this problem of AC optimal power flow that we just talked about. And the goal is that if we're able to solve AC optimal power flow or other problems to manage power grids in real time and at larger scale, that allows us to better integrate time-varying renewables, which, since those vary over time, having real-time solutions is helpful, as well as improving the robustness of the power grid and reducing waste. The challenge is that existing solvers for AC optimal power flow are really slow. And so they don't solve fast enough to deal with the real-time nature of renewables, and they don't solve at large enough scale to deal with the fact that we have many more renewables and distributed devices coming onto the power grid. And so the approaches that are used are, a combination of optimization and machine learning. And there are various approaches that both try to directly speed up the AC optimal power flow problem using machine learning. And you can go ahead to the next bullet. And so that's things like predicting constraints in AC optimal power flow that might be redundant, or learning better starting points for optimization solvers, or even learning full end-to-end approximations for AC optimal power flow. And the tutorial for this week on power systems will actually deal with this first bullet of machine learning for speeding up AC OPF. And there are also various techniques that try to use reinforcement learning instead of solving the centralized optimization problem in a standard way, actually use reinforcement learning to suggest what actions to take on the power grid. In addition to optimizing power grids in a centralized way, power grids can also, as we mentioned before, right, be operated in a distributed or decentralized way. And machine learning can play a role in helping to actually control those distributed resources like solar inverters, like batteries, like flexible loads, where the need is that we need control strategies that are, fast, flexible, scalable, robust, physically feasible. So they have to work well, and they have to satisfy the constraints of the engineering system. And so the approaches that are taken are often a combination of machine learning and control theory, where machine learning can often come up with very powerful and well-performing strategies for distributed control, but where the challenge is that machine learning techniques don't tend to come with robustness guarantees or provable guarantees, which, if you don't have those things, can mean that you black out your power grid. So there have been a lot of works that try to combine machine learning and control theory in order to deal with this. And so the general idea is that if you have, kind of some control theoretic controllers that have some provable guarantees, and you have machine learning methods that can learn from data, then you can do things like take the outputs of the robust control model and the machine learning model and choose which one you're going to use at a given point in time, or mix between them. Or you can even embed control theoretic constraints into the design of your reinforcement learning models in the first place. One thing we forgot to mention is on these slides, there are some citations in this kind of box letter year format. And so the slides will be shared with you after, and there's a references section at the end in case you want to follow up on any of the citations in here. And kind of the last category of applications I want to cover is predictive maintenance and efficiency improvement. So this idea that when we're operating a power system, sometimes things break, sometimes things are inefficient. And if we can detect those inefficiencies or outages ahead of time or in real time, then that can help us operate the system more efficiently. And so machine learning is used in this context alongside to analyze large amounts of data on the power grid in order to figure out where there might be efficiencies, in addition to approaches like manually inspecting the power grid and traditional signal processing approaches. And so some examples here include detecting methane leaks in natural gas infrastructure. So as natural gas is transported in pipelines and in compressor stations from where it's extracted to where it's consumed, there have been efforts to use a combination of satellite imagery and even sensors outfitted on the natural gas infrastructure in order to actually detect where there might be anomalies or where you might actually see methane leaking using the satellite imagery. In addition, there are lots of applications that similarly try to detect anomalies in solar power production, wind turbines, batteries, or also identify places where there might be theft of electricity on the power grid by basically analyzing and trying to find anomalies and patterns in the underlying data. So having talked through machine learning for operations in power grids, I'm going to hand it over to Simone now, finally, to talk about some of the other ways that machine learning plays a role.
So the next area that we'll be looking at is the planning area, though subsequently we'll cover innovations policy and data management. So the goal with planning in power systems here is either the design or construction of new infrastructure or reinforcing the existing backbone. It could be transmission backbone, distribution backbone. So here with planning, you want to be able to incorporate low carbon sources, like I mentioned, reinforce your existing connections and ensure that you have high reliability in terms of service provision for the consumers. And some ways that planning is usually done, or some approaches that I use for the different dimensions of planning can be multi-objective optimization. So where do you place your resources? Where do you place your assets? How do you design the lines? Where should the lines actually go, depending on where your customers are? It could also touch on estimating demand, so doing manual surveying to see how much demand might be in the area. It can also mean consensus building in sense what systems do the consumers actually want to have. Is it a microgrid? Is it a centralized grid in the system? So there are multiple dimensions of planning, and some examples that we see that machine learning has been able to support has been one in helping understand grid topology, so mapping out lines and solar wind infrastructure to understand how you can provide services from renewable energy. The other aspect has been in demand estimation, especially for new consumers, and capturing the uncertainty that might occur when estimating the potential demand that a new customer might have on the grid. Another application area that we see gaining some traction for machine learning applications is in the innovation space. And by innovations, what we mean is either in the development of low carbon energy sources, or more effectively improving energy storage and efficiency, or sequestration of greenhouse gases. Here, in the case of CO2 sequestration, even energy storage, we find that typical approaches are for like human-guided experiments, sometimes in a wet lab, sometimes through simulation, but we're seeing machine learning increasingly being used to help discover new viable battery chemistries, for example, that can lead to fewer experiments being run and finding the right a set of chemistries that lead to better battery behavior, battery performance. There's also some work that we've seen being done where for nuclear fusion reactions, sometimes the generation of plasma can cause disruptions due to just the instability in the plasma. So there's work being done in predicting where disruptions might occur in your reactor, as disruptions can cause damage to your equipment. So they want to be able to predict where those disruptions might occur and deploy disruption management systems ahead of time to prevent those disruptions from kicking in. So that's another dimension where machine learning has also been called on for innovation purposes. Another aspect also in terms of the power grid has been in how we design policies, regulations, and also how we monitor the impact of these policies on markets and any downstream from there. This has typically taken place in the form of either policy analysis, market studies, doing market design, but now we're seeing machine learning being increasingly called to supplement some of these approaches. So there's been some work in understanding how trends in the solar power space have shifted, even analyzing the patterns. And this actually reveals gaps of where the market could either go or where technology didn't necessarily do well in addressing some of the challenges that we face. So this can influence how we design, say, solar policies or solar power plant policies that can improve adoption of low carbon sources. Another area too has been in leveraging reinforcement learning to set market prices. Here there's some work where they use reinforcement learning and deep neural networks to determine the right prices that could reduce the peak to average ratio, and understanding how different either microgrids would respond to different prices. It's a good way to understand the impact of different prices on the market and how to adjust the policy based off of behavior. Another area too is in data management. We're increasingly observing that utilities, energy providers are handling more and more data, either through the deployment of smart meters and better compute that's available, but not as much work has been put forth to advance data usability. So we're seeing machine learning being called to facilitate data cleaning, compression, condensation, and processing. As opposed to doing manual cleaning or the traditional, say, data compression strategies, ML is being used, for example, in the case by Catalyst Cooperative, where they do record matching between data sets on US electricity data, say FERC and EIA, that are usually hard to match independently. So these are posted independently, but can be hard, even though they might be referring to the same power plant, the same generators, it's hard to match them. So they actually develop a model that can help match them so that there's more cohesive view of the landscape. So we've tried to give you a brief run through on like the different areas within power energy systems where machine learning is being utilized, but we will go into some case studies a little bit later on in this presentation. For now, we want to take a step back and ask you, what do you guys think are some important things that we need to keep in mind when we use machine learning in the energy and power systems? What are some things that are important for us to either implement or consider? And feel free to drop your answers in the chat.
Just wanted to raise a question that's posed in the Q&A. This comes from Jeff Sovich, which asks, what is the typical reaction time that is needed in optimizing power flow? For example, how quickly does a generation facility need to be able to reduce generation in order to avoid a dangerous imbalance?
So this is a great question, and the maybe unsatisfying answer is it depends. So to give a little more qualification on that, in the US, we operate the power grid at a frequency of about 60 hertz. And so if your frequency changes based on how much supply-demand imbalance you have. So if you have more supply than demand, your frequency is higher. If you have more demand than supply, your frequency is lower. And if your frequency is off by kind of a fraction of a hertz or a hundredth or something like that, then you have a couple of seconds to get that back, and they're often kind of automatic mechanisms installed in power plants to detect when there's a small mismatch in the frequency, where each power generator has then like a little bit of a fractional responsibility to help make up that difference. But if you have, a very large frequency difference, like, it hopefully never gets this extreme, but, 55 hertz on a 60 hertz system, you definitely don't even have a second. You have much, much, much less than that. And one thing that's challenging is that there's a concept called system inertia, which comes from the fact that conventional power generators have spinning components that are synchronized to the frequency of the power grid. And if there's a mismatch in supply and demand, it actually takes a little bit of time for those spinning components to speed up or slow down. Whereas with solar power and kind of other sources that don't have that spinning component, they're not providing that buffer to the system. And that means that in systems with larger amounts of kind of non-spinning power generation, mismatches in supply and demand can lead to much faster swings in the frequency of the system. So what we're actually seeing is that as we move towards more renewable energy-based systems, the amount of time we have to respond is even less. And that's driving some of the need for kind of automation, because we're now starting to talk truly sub-second scales where it's really hard for a human to respond that quickly.
I think we have another question in the chat, which says, beyond AI or perhaps combination, are there any traditional applications of network science and graph theory in energy space? I think for planning, there's quite a bit of graph theory that might be called upon there, especially on how you do connections between, say, your distribution and transmission infrastructure. How do you connect households? Actually, how do you connect low voltage lines from households to your substations, the feeders, all of that in an optimal way where you're minimizing the cost and not just going as the crow flies. So I've seen quite some work in terms of like graph theory for that type of research. Priya, feel free to add to it before we.
No, that sounds great. Feel free to keep going.
Good. Also, given the comments in the chat, I think a lot of comments here align with some of our thoughts. One is around the data reliability, data access, integration with existing systems, data quality, domain expertise, which is a huge point, respecting physical constraints, cybersecurity. All of these are really great considerations. I'm glad you guys have been able to call those out. And to that point, what we're trying to get at here is that electricity grids actually have physical laws that they have to meet, meaning in a simplest form, it could be matching supply and demand at every point in time, like Priya mentioned. It could be respecting the limits of the line. So there are actually operational and physical laws that have to be respected, and even how like electrons flow throughout the grid. And so when we call on or when we utilize machine learning in this space, we have to make sure that whatever outcomes that we have are in line with how a grid can be actually operated rather. And to do that, there are a few things that we need to think about, as mentioned in the chat, when using machine learning. One is around safety and robustness. Is the solution going to lead to cascading failures in our grid? We need to make sure that whatever the ML model outputs, we're able to respect safety constraints for the grid. We also need to ensure that we're still robust. The grid is still robust. It can still handle disruptions and whatever solutions we come up with. Are the solutions feasible? Yes, we might come up with a minimal cost solution, but does it actually respect the line limits, or is it requiring more power flow than the line can actually like hold? So there's this physical feasibility of the actual solutions that can be put out by the model. Do we understand the drivers or the levers for that output? And do we have control over them? So can we understand what shifts the decision from one prediction to the other, and do we have control over that? So, for example, when we're predicting demand, do we understand why the demand is being predicted that way? Is it what latent information within the data is it learning from to make that prediction? And do we have the right knobs to be able to control that? Do the outputs from the models meet regulatory standards? There are different regulatory standards depending on where you are, and it's very important that the ML models respect those regulatory standards for safety, for and robustness of operation. There are already existing methods too for different power energy system problems, whether in predictive maintenance, whether in predicting generation. There's already some some performance measures that the baselines are already meeting. So the machine learning methods really have to provide a case for why there should be a switch to the ML method. It could be they're doing better than the state of the art there. It could be that they're faster to run, they require less time, but we need to be clear why we want to be able to switch and what metrics we use to determine that the ML model is a viable alternative. As mentioned throughout this lecture or discussion, there's different infrastructure throughout the grid, be it the SCADA systems, the different smart meters at the consumer level. So whichever model that we're using, can it easily integrate with the existing infrastructure, or does it require an overhaul to acquire new infrastructure? And this can really be prohibitive, especially for emerging economies where our resources are particularly constrained. We need to ensure that whatever outputs we have can be directly integrated to existing infrastructure. Is the model usable? Is it accessible? Can stakeholders who actually make decisions, say the grid operator, can they actually use the output from this model or use the model and understand what it means, or is it just a one-time thing that they can have access to? Another aspect is also preserving privacy. It's quite important, both privacy for consumers, but also for the safety of the grid and prevention from like bad actors. Are we making sure that whatever the ML work we're doing with ML methods are preserving privacy of users or of assets is also very important. Finally, while there's been development in a lot of ML methods, it might not necessarily always be the case to develop never satisfiable data hungry methods that. And I think this is where the opportunity for like physics informed machine learning really comes into place. Like, are we using the data efficiently to be for the space? I would say are some key considerations in this space. Now that we've looked at what to think about when developing ML methods, we will go into a few case studies to see how we can contextualize some of these thoughts within work that has been done out there. So starting off with this graphic, I'd say when we think about using machine learning models or methods in power energy system, and really any domain, one of the first things that come to mind is what data set do we have and what method are we going to use? Most times is what is the newest and brightest method even that we can use given this really cool data set that we have. But what we're trying to advocate for, especially if the objective is to have impact, is to take a step back and actually think, if we were to ideally solve this problem, who would care and why should they care about it? So understanding, okay, what domain are we in? How do we scope this project? Who are the people that will care if we solve this? And for them to care, what metrics are they interested in? When the model is developed, how do we analyze that the outputs from this model actually meets the metrics that they care about? Can the model be deployed? Is it usable? And what are the impacts? And this is really not just even like a one-time analysis. It's something that we have to sort of go through multiple times as we better understand or grasp what the objective of the project is and what impact might look like. And it is through this lens that we want to be able to look at some of the case studies and see how we can think about it along this framework or this mental model. So the first case study that we will look at is mapping utility scale solar in India. Again, the reference formats, you can access the actual papers, given the reference format at the end of the lecture. But the idea here is that India has a goal of renewable or 500 gigawatts of renewable energy capacity by 2030 and net zero emissions by 2070. And here, there was no clear way of understanding, okay, how well are we meeting that objective that we've set for ourselves. So there was no comprehensive data set on like geospatial information for utility scale solar across the country. So it's really hard to evaluate, are we meeting the goal that we've set for ourselves. So one approach that the authors could have gone about would be to try to collate this information from different utilities. But you can see how this can be somewhat laborious and time consuming to do this either from a survey standpoint or manually collating this information. So they opted to do detection of utility scale solar using satellite imagery. Here, the objective was by detecting utility scale solar, they can figure out or can better support where to place transmission lines, where to actually invest in transmission to be able to support grid integration of these renewables. You can monitor progress towards the targets that one has set for themselves, especially over time, and can quantify what the impact would be of placing utility scale solar on different land use types. So who would care about this kind of work? It would be energy planners, policymakers who set this target, even utilities who are planning out asset expansion, like we've mentioned in previous slides. So to do this, they started off with a small data set of solar PV farms that served as labels, and they used multispectral Sentinel-2 imagery to learn and train the models. And what they did was if I may say, human-machine collaborative approach where they did some clustering to obtain weak labels of where utility scale solar might exist. And then from these weak labels, they were able to then train a supervised segmentation model for detecting these farms. From their work, they report a standard machine learning metrics. So things that you do with segmentation, say like intersection over union, precision, recall, given the way the problem was formulated and set up. But then they also try to report other metrics that decision makers might actually care about. So where are these PV or where are these utility scale solar plants located? What is the size? When were they deployed? What was the impact on land use and land cover? These are actually metrics that a decision maker can take and say, okay, this is how it affected the economy or affected where we placed solar. The thing to note about this work is figuring out, even though they were able to detect utility solar, where are the boundaries of this work? So there's a focus on PV footprint over power-related metrics, over power-related metrics. So rather than saying that, or even energy-related metrics, rather than saying that, oh, the plant is operating at this capacity, that's beyond the scope of this work. So understanding where the boundaries are of the work can also help the work. Some deployment considerations were how this approach might differ regionally. How sensitive is it to panel sizes?
Simone, I think we're losing your audio on and off. Maybe your headset is dying.
Oh, hello, can you hear me?
Yes, I think we're hearing you on and off a little bit.
Okay, hopefully it shouldn't be dying, but I'll give it one last try and then I'll switch off if it does. So yeah, sorry about that, by the way, guys. And these authors have actually extended this work to also consider wind power plants in what they've termed as Global Renewables Watch. A downstream effect that we would need to keep in mind is what are the implications of sharing the location for generation assets. This could either be like safety implications, but it's something that they might need to think about in how they disseminate or share this information with different stakeholders. Before I move to this case study, is the audio better?
Yes, much better.
Okay, thank you. Awesome. So the next case study that we will look at is one around climate model projections and downscaling solar irradiance from coarse to finer resolution outputs. Here, the authors are interested in better supporting planning of renewable energy production, given changes in climate change. And the argument that they make is that with the availability of coarser resolution estimates, it's harder to plan for renewable energy production, especially as the climate is changing. And so there's a need to have higher resolution of finer grain estimates to really capture the local differences that might occur when estimating the amount of renewable energy that can be produced in a location. So the lack of downscaled data or higher resolution or coarser resolution data was the problem here. And one way is just to use the historical available data, but then one isn't capturing the changes that may have occurred that are now reflective in how much power can be generated. The other approach is to use finer grain climate models, but those can be very computationally intensive. So they're proposing an enhanced way of getting to higher resolution outputs without high computational costs. The pathway to impact here, meaning that why this would matter, why this would be important, is that these higher or finer grain outputs can be used for power systems planning, but can also capture the local differences that might occur, that might be lost when you're dealing with coarser resolution outputs. And who would care? System planners, utilities, generators, anyone more or less interested in low carbon energy adoption would be a viable candidate to care about this. From a dataset standpoint, they use the core scale climate model outputs of solar irradiance, and as the input of like coarse resolution data, and as the output or training signal, they provide the fine-grained reanalysis solar irradiance product. So here it's a self-supervised deep learning modeling approach where they are more or less predicting with sub-pixel convolutions a finer scale and then comparing it to the true one, and that, like I mentioned, serves as the training signal. The metrics that they use are the root mean square error, which is good metric for this, but they also use what they call a structural similarity index measure. And the idea here is that with the mean square error, there was so much smoothing occurring that you were losing the local differences that might occur. And that was one of the motivators of the work anyway. So they explicitly put in this metric to be able to capture how well we're doing in the local differences that might be present. For the boundaries of this method, it's really dependent on having good supervisory data, and the data came mostly from the US, but when shifting to data poor areas, then the methodology might not necessarily be as applicable or might need to be modified to adapt to that scenario. And while they did spatial resolution work, they didn't do a temporal resolution work. So can they go from a lower temporal scale to a higher temporal scale? That might be another dimension that the method might not necessarily apply. Also, though the objective was on better supporting planning for renewable integration, it didn't consider, maybe an out of scope of the work, it didn't necessarily consider the grid constraints given existing infrastructure, which is fine, but it's just about understanding where the boundaries of the work might lay and how to use it. At the end, the questions that they'd have to also answer is, in terms of deployment, is can people easily access this data set or use it, or use insights from this data set? How accessible is it for someone who is interested in replicating such work to be able to access the outputs, and replicate the work? And finally, what the implications would be for different stakeholders when carrying out planning for renewable energy integration. I'll pause here for Priya to hop in on the next case study.
All right, so we're gonna go through 2 more case studies and then a few more quick closing thoughts, and then we'll be opening it up to your questions. So feel free to also be gearing up with some questions in the chat or in the Q&A if you'd like. So the next case study we want to talk about is reinforcement learning for topology switching. So the basic idea here, next bullet, is that we need to increase the utilization of renewables on the power grid and also adapt to extreme events that might happen on the power grid. But the challenge, as we've discussed before, next point, is that, and you can keep going, that existing power grid optimization methods are not dynamic enough or robust enough or fast enough, as we talked about before. And in addition, even as we try to develop new methods, there doesn't tend to be as much, good simulation infrastructure that really shows us what's actually happening on power grids. And this means that we're not able to properly validate our methods or deploy our methods or develop them in a way that is really contending with the real factors of the power grid. And so some possible approaches to deal with this include, optimization methods, control theory methods, or data-driven methods on the methodology side for the optimization. And on the infrastructure side, next bullet, the kind of approaches involve trying to create better simulators or test beds, or even, I'll use the buzzword digital twins of the power grid in order to help us actually develop methods and validate methods for power grid optimization. And so the pathway to impact here is that we ideally want these methods to ultimately be used by the power system operator, either autonomously or human in the loop, where there's a control operator who's giving high-level actions and guidance, and where the machine learning algorithm is executing those strategies on a lower level, for example, on a sub-second time scale. And the stakeholders here involve a combination of power grid operators and, for example, software providers that might actually, power grid operators often tend to procure software from various companies to actually help manage their system. So working with those software providers to actually integrate some of these techniques into the software is one potential kind of pathway to deployment. So one project that's dealing with this is the Learning to Run a Power Network Challenge, or L2RPN, which is run by the French power grid operator, the Electric Power Research Institute, and a bunch of other additional power grid operators and both academic and non-academic stakeholders. And what this initiative is a series of challenges where they try to validate the use of reinforcement learning to optimize power grids, and where they provide a simulator. And if we actually go to the next bullet and the next one after that, they provide a simulator called Grid2Op, which is actually a reinforcement learning style simulator that tries to mirror some of the things that are challenging about optimizing power grids. In addition to that, that when you have a simulator, that simulator has to have some data actually infused or injected within it. And so this involves a combination of what is the structure of the grid, what is the electricity demand and supply on the grid, and the data sets here, some of them are synthetic and some of them are reflective of the French power system. And the machine learning approach here is a variety of methods. So through the competition series, people have submitted a large kind of variety of reinforcement learning methods, almost all of which use some combination of pure data-driven learning alongside heuristics about what power grid operators actually do today, alongside some physical knowledge of power grid physics and how the grid actually works. Now, how do you know whether a method is actually good, right? How do you know if you're optimizing the power grid well? So kind of similar to some of the considerations we talked about with AC optimal power flow, we care about the cost or the price associated with the solution. In addition, we care about the physical robustness of the solution. So when I'm optimizing the power grid using reinforcement learning, does the power grid actually survive? Does it stay up or does it black out? And in addition, we care about the speed of these methods. The reason that we're using machine learning in this context is because we need faster and more real-time methods, which traditional optimization problems or solvers are struggling with. And so we also need to assess the speed of the solutions that we're producing. The kind of boundaries of the methodology is in large part that a lot of these methods are still early stage. So they still are, the simulators and the methods developed on top of them are still generally optimizing relatively small power grids and using synthetic data. So they don't capture the full scale and realism of the system. And also, even though in some cases, the goal is to try to use these human in the loop. So the machine learning algorithm suggests something and the power grid operator suggests something. Right now, the simulation environments are not taking that human in the loop capability into account. And there are lots of deployment considerations that are then needing to be captured there. Different control rooms in different power grids work differently. And also different power grids are operated more centrally or in more of a decentralized manner or in a mix. And the existing simulators tend to suggest that you're doing a kind of centralized power grid optimization. And in terms of the downstream effects, when you're using machine learning, reinforcement learning on a power grid, there are lots of implications for pricing, right? Are you investing a lot of money in sensors and advanced software and such, and that might increase power prices? Implications depending on whether you're thinking fully automated control or human in the loop control for the jobs of system operators. Reinforcement learning can facilitate a change in market structures, for example, from fully centralized markets to potentially decentralized markets. And a potential downstream effect is also when you're optimizing a power grid and making a power grid more efficient, you're also helping make it more efficient for every single resource that's on the grid. So that can benefit renewables, but that can also benefit fossil fuel generators. So it's important to understand sort of which power grid optimization progress is facilitating renewables integration versus which is maybe actually neutral in this respect. All right. So a last example I'm going to give here is about actually using machine learning to create data, which in some cases, again, seems a little counterintuitive because machine learning relies on data. But there are certain situations where we maybe don't have access to the real data because it might be private, because it might be protected in certain ways. And yet we're having a publicly available data set is very helpful for research and for policy analysis and for other actions that allow us to decarbonize the power grid. So one example in the next bullet is, or actually you can go on 3 more bullets. So basically, given this need to have public energy systems data, but where there are sometimes regulatory or cultural barriers to sharing this data or privacy issues, one possible approach is to create synthetic data, either manually, you can look at your real data, identify what makes that data look like that data. So if I have a data set of electricity consumption collected via smart meters from consumers, I can look at that and maybe say, okay, the data has a certain shape in general, it has a certain peak at this point in time, and you can try to replicate that manually, or you can try to use automated techniques to try to figure out the distribution of the underlying data and replicate that in synthetic data. The other approach is to facilitate sharing of real data. And that can be through technical methods like adding noise to the underlying data in a way that maybe makes it realistic enough, but maybe protects it enough, or also via policy or organizational changes. Sometimes data is not shared, not because of any actual technical or socio-technical reason associated with the data itself, but rather because it's hard. It takes effort to clean data, to host it. And so, of course, this is an important thing to consider as well. And the pathway to impact here is that you kind of want to ensure that data ultimately is available for use by, researchers, by decision makers, by market participants, many other entities. And this can be either through public release or in some cases controlled release, where someone can request access to data and there's some process to verifying whether they'll use that data appropriately. So one approach that has gone the synthetic data route and the machine learning route here is a project called Faraday by the Center for Net Zero. And what they're trying to do is actually take data sets of real smart meter data, which they have access to due to their particular business, which involves actually working with customers to make their demand more flexible. They have access to a lot of private smart meter data, but they can't release it because of privacy and regulatory concerns. And so the question is, can they actually leverage that data set to produce synthetic data that doesn't have privacy leaks, but that does allow kind of research and the policy community to work with realistic data? And so what they do from a data set perspective is that they have a proprietary data set of over 300 million smart meter readings coming from Octopus Energy, which is an entity that they're affiliated with. And their approach is basically to train a specific type of autoencoder model, a conditional variational encoder, autoencoder, to map this training data to a latent space, which basically means look at the data and try to figure out a kind of smaller dimension, fixed dimensional representation that captures the axes of variation in that data. And then having mapped information to that latent space, they train a machine learning model on top of that to learn that distribution of the data. And then they sample, next bullet, from that particular machine learning model and pass it through a decoder to basically say, okay, I'm now going to be able to sample new data points that look like my old data points in some high level way. So when you're starting to generate synthetic data using a machine learning model, you have to be really careful that you understand what it means for that data to be good. Because if you imagine this nightmare scenario where you generate synthetic data using a machine learning model, and then you use another machine learning model to analyze that synthetic data, and your data is bad and your downstream machine learning model is doing some stuff that's imperfect, that can be like a horrible game of telephone for those who played this game as a kid, where you whisper a phrase into your friend's ear and then the friend whispers it to the next person. And by the end of the circle, the phrase gets very changed from what it was. You want to make sure that you're not propagating errors by kind of having a bunch of machine learning models in a row that are feeding off of each other's outputs. And so you really need to understand, in this case of synthetic data, how do I know that the data is good? And there are a couple of different metrics that are used here. One of them is fidelity. So can I calculate some statistics about the original data? And does the synthetic data have those same statistics? Does it have the same mean? Does it have the same variance? If there are physics properties associated with the data, are those preserved in the synthetic data? The other metric is utility, in the sense of usefulness. So when I use the synthetic data for a real life application, does it actually provide reasonable insights, or does it give me the wrong answer? So if I use the synthetic data to ask the question of how much solar power should I install on my grid in the future, and I use the private data to ask the same question, the answer shouldn't be so far off from each other, because otherwise you actually have not produced a good synthetic data set for the purposes of power grid planning. And then a third metric, and an important one, is privacy. Is the original and private data exposed? Now, the boundaries of the methodology is, as much as we can write down these metrics, first, we actually have to get better about writing down these metrics in order to fully flesh out exactly what you need to measure to understand these aspects. But it's also an open question. How do you actually verify that those metrics have been ensured? Or how do you actually construct models in a way that ensure those metrics? And there are some deployment considerations here as well, in that there are trade-offs behind the above metrics. You can imagine that if you have data that's very high fidelity, it might be more prone to leaking privacy. In some sense, the highest fidelity synthetic data set is one that is exactly equal to the original real data set, but then that's exactly the wrong move in terms of privacy. So really thinking through for your particular use case, what's the right trade-off between fidelity, utility, and privacy? That is an important deployment consideration, both in the context of a particular use case and overall. And of course, there are various regulatory requirements, various issues of trust, and questions of who can access and use the data in practice, which some folks say we want to try to get these methods to be good enough that you can fully publicly release data. Others say we're never going to get there, but maybe we can do controlled releases where people can request access to this data. And then a kind of downstream effect of this is that if you make data fully publicly available, that improves access for everyone. But that means, quote unquote, improved access for both good actors and bad actors. And so it's worth, again, thinking about the implications of that when doing data release. So we talked through a bunch of different case studies here for the use of AI in power and energy systems. And before we kind of move on to our kind of closing here, one thing we want to emphasize is that very far back in the intro lecture of the summer school, we talked about various ways in which responsible AI is an important consideration to think about in the context of climate change related applications. And this is true in the context of power and energy systems as well. When earlier Simone asked about what are important considerations to think about with respect to ML in power systems, many of the considerations that many of you dropped in the chat hit on a lot of these considerations. And so that's really great. And so just to recap really quickly from the intro lecture, we want to make sure, first bullet, that we are cognizant of the ways in which biases may affect the data that we're using, the models that we're creating, and the context in which we're using those models, thinking about things like geographic disparity in data availability. We also want to think about, next bullet, the importance of trustworthiness and accountability in our models. So we've talked about ways that safety and robustness are really important when optimizing a physical system. But also there are various ways in which, as we talked about, interpretability and auditability are really important, because if something goes wrong on the power grid, we need to be able to understand why that happened. In addition, it's important to think about the ways that our use of AI and machine learning in the power systems and energy systems context interplays with various aspects of, who holds societal, clout and power, and who already has access to money, for example. So it's important to ensure that these methods are deployed developed and deployed alongside and with a diverse set of stakeholders, and that the way these methods are deployed doesn't centralize power or exacerbate existing issues of colonialism. So for example, smart meter data in different countries has different privacy protections associated with it. And so we shouldn't, for example, just train machine learning methods on models associated with countries that have not put privacy protections in place. Instead, we should really think about this issue in a more kind of equitable way. And these considerations are not exhaustive, and there are a lot to think about. So of course, there is a huge importance to working with relevant stakeholders throughout the entire development and deployment pipeline. And this is why kind of throughout our case studies, sort of throughout the introduction to power systems, we try to outline who some of those stakeholders might be. And for any project that you're working on, it's abundantly important to think that through right from the get-go to make sure that you're shaping your project with that consideration very deeply in mind. Okay, so we're gonna wrap up here, and then I think we'll have a few minutes for questions at the end, but we wanted to talk through kind of next steps and talk through our journeys into this space as maybe an example of what those steps might look like. So my own journey into machine learning and power systems is that as a high schooler, I got very, excited and interested about working on climate change. But then in undergrad, I got very interested in computer science. And at the time, it was really unclear to me how those two things connected to each other. Luckily, a group of researchers in the UK had put together a paper talking about how AI would be critical for power grids. And I got very excited about that area. And then initiatives like the Computational Sustainability Network, communities that really brought together researchers who cared about the intersection of computer science and sustainability. Those kinds of communities were really valuable to me. And some of what kind of climate change AI is trying to provide is this kind of thing. And so definitely, if you're interested in this area, I very much encourage you to connect with your fellow summer school attendees and otherwise, take advantage of this community that's here. In terms of positions and collaborations, I think, both my research and academic journey was very helpful in doing this work, but definitely, various internships at, US national labs that work closely with power grid operators, as well as at power system operators like National Grid ESO. Those really shaped my perspective on the problems that are actually being faced in the industry to ensure that my work in academia was really contending with those. So this idea of, no matter where you're doing your work, if you're doing your work in academia, if you're doing your work in industry, I think trying to kind of work across and collaborate across those sectors can be really important in gaining the perspectives that are necessary to do this work well. And in terms of sort of top tips I would give, take classes in multiple disciplines. So if you're a student, you'll notice that, a lot of the things we talked about here, some of them are about electrical engineering, some of them are about computer science, some of them are about policy and regulation. Really engaging with these different areas can be quite important to actually, working in this kind of space. And in addition, kind of internships and secondments or attending conferences hosted by different communities can be other ways to really understand the kind of interdisciplinary perspectives that are necessary to do work in this area. Engaging with local and community organizations is also really one way to do work in this area. So for example, there are many cities that actually have, energy advocacy groups or local electricity cooperatives, and kind of engaging with those groups can be one way to work in this space. And in general, again, take advantage of the community around you, reach out to people, kind of, for example, others were taking the summer school or more broadly. And when you do that outreach, do your homework. Don't send a random note, but instead kind of engage with what that person has done and understand how you might actually work together in more detail.
I think for my journey into ML and power systems, my formative experiences around electricity access, reliability, and low energy carbon sources really just came, I would say, more experiential. I am from Cameroon, but I lived in multiple places throughout sub-Saharan Africa. So just being able to understand what were the common threads around energy access, reliability, and power systems in these different areas sort of sparked my interest in this space. And I was really able to engage with it then as I did my master's and PhD. One thing that I think helped me sort of concretize or formalize my interest and maybe work in this space was doing internships that were true to both the problems I wanted to solve and the methods I wanted to use. So for example, being able to work on power energy systems style problems and also leveraging computer science algorithms and principles, I think helped me figure out which places to do an internship and eventually join as a researcher. I also spent some time with working with different stakeholders, and maybe that'll be alongside some of my tips. I worked with Kenya Power, REG, Umemi, which are all utilities, to understand the challenges that they were facing, the problems that they wanted to answer, and how we could use ML and data to help them. So my number one tip is find something that you actually care about. I know that it can be hard to try to answer the question in a vacuum. So to be able to figure out what you care about, I'd say it starts from trying out different things. So participate in competitions, do some literature review, learn more about the different aspects and domains. Thanks for attending the summer school on power and energy systems. But those will all go to like build your knowledge and intuition bank on what you care about and what you should actually spend more time doing. For me, I particularly found competitions very helpful because it helped me merge domain knowledge with really the computational skills to be able to apply ML in this aspect. And then engage stakeholders, actually talking to utilities, working with them, helped me figure out what problems they really care about, what problems I thought they care about, but that they don't. So it really helps hone in on what you should be spending your time on if you want to have impact. And then finally enjoy the process and don't necessarily put pressure on yourself to have it figured out upfront, but rather think of it more as a journey, which I'm still also currently learning from. In terms of resources, we wanted to provide you some hopefully starting points on either data sets, resources, simulators that you can hopefully ignite your journey with. On our CCAI wiki, we have an electricity systems page that lists out a bunch of data sets, a bit of background, and really the different aspects that come into play when thinking about power and energy systems. So I would encourage you to go through this page and learn more as maybe a starting place for the journey. For some open data sets, there's the Open Energy Data Initiative from the Department of Energy. And while this data set is very US focus or US centric, it's not necessarily a bad place to test out different approaches to build intuition, to hone skills. So I would also encourage you to go on there. There's over maybe 3 petabytes of data on there. So there's really quite a variety of things that you can engage with there. Priya mentioned IEEE data sets, and that's another space that you can go to for simulators, data sets to test out some of your algorithms or to build some algorithms out. And we're also working on updating the wish list, but there is a base version there that you can see what the linkages are between different data sets, the type of ML methods that you can apply to those problems, data sets, and what climate relevant problem they'll be trying to address. So that's another resource you can utilize. If you're looking for community, which Priya encouraged us to do, there's the CCAI community platform, and specifically the power energy space, which is a good place to find like-minded people interested in topics or potential collaborators that you can work with. And if you look specifically at the power energy tag in our newsletter, you'll be kept up to date with some of the information that we have on the changes that are occurring in this space. At this point, maybe while people can take a minute to post what your next steps would be in either ML and climate change or ML and energy journey, we're interested in learning more about what that would be, but we might also take this moment to answer a few questions before we are out of time.
And then alongside posting that in the chat, we're also happy to start answering questions, but we're definitely very curious to hear what you might do with the information you learned today.
Given that we're running a bit out of time. We'll do our best to answer the questions posted in the Q&A by typing, so that that way we can answer as many questions as possible. Also, just a reminder that we've posted the form for the Google form for feedback in the chat, so please take a moment to fill that out when you have the chance. Priya and Simone, do you have maybe a bit of time to answer some questions live to stay on? If you do, okay, fantastic. So there are still a couple of open questions in the Q&A. I think that would be nice to answer live. So we'll just go in order. So one of the questions that was posed earlier on was, what are some resources to design microgrids?
Good question. I actually don't have a great answer to this since I don't work in the power grid design space. I don't know, Simone, if you have any thoughts.
Not off the top of my head. There are components to microgrid design, but not off the top of my head. No, I don't have a good resource for it.
Would you have any pointers for other people or places to look for resources for that?
Design microgrids.
My starting point for this would always be in literature. Yeah, and again would be to figure out what aspect of microgrid design am I focused on. Is it in the interconnectedness? Is it in the planning phase of power generation relative to consumers? Yeah, I'll try to hone down on what aspect I'm interested in, and then my starting point will always be literature.
And I just Googling around, I saw some initial, one link from the US Department of Energy called the Microgrid Design Toolkit. So I have not used it before, but I put a link in the as a response to the question in case it's something worth looking into.
Great. Thank you. There's also a question on, let's see, for downscaling solar radiance case studies. So this is one of the case studies. Are there follow-on papers that do temporal prediction?
That's actually a good question. I haven't looked into temporal prediction using that study that we mentioned. Priya, are you familiar? But what I might suggest is we do put the reference, which we'll share. And once you put that, you can check the citations and specifically look into that. But I can also quickly check to see if there were any follow-ups on temporal prediction.
Great. Thanks. There's two questions from Yusra. First question is, if we only have a meteorological data set, how can we use them to carry out studies on forecasting for renewable energy, apart from a simple weather forecast to manage a system?
Yeah, so this is a situation where, in principle, if you don't have historical data on renewable energy production, what you want to somehow try to do is match your meteorological forecast with knowledge of, for example, where specifically are there solar panels on the ground and what is their capacity, or where exactly are the wind turbines on the ground and what is their capacity. Now, of course, this data is not always readily available either. In principle, you would ideally survey different kind of renewable energy providers and owners of power generation infrastructure to figure this out. But some of the work that Simone talked about in terms of, for example, detecting solar panels from satellite imagery and trying to understand or estimate their capacity from that can be an intermediate approach where then you use your meteorological data alongside maybe a satellite imagery derived estimate of what your on the ground solar capacity is. And then you kind of match those up to infer what you think the solar power production would be. There are some challenges with that, right? Because, for example, solar power production is highly influenced by cloud cover, and maybe you don't fully have that information, but maybe you can infer that from historical satellite imagery as well. So in this case, it does end up being kind of stitching together multiple sources of data that give you different pieces of information and trying to figure out what together those might imply.
Priya, actually bring up a good point around like the work that, if I may say, leads to research outputs versus the work that actually leads to practical usage of say AI models. Like you mentioned, the actual deployment might be a combination of multiple things to get to a working solution.
Great, thank you. Another question by Yusra, which is how can we manage the renewable energy production using IA, which I take to be AI, and forecasting? What are the methods and strategies?
Yeah, so there's two ways to think about when you already have renewable energy resources, how to manage them. So one of them is, as we talked about, AI and machine learning for forecasting. So if you have more insight and foresight on how much renewable energy you have, that allows you to do things like flexibly change how much electricity is being consumed at a given time using strategies like demand response in a way that is matched with the amount of renewable energy supply that's actually available. The other option you have is to, if you, for example, have too much energy on the grid, you can curtail or basically waste solar or wind power, for example, that's available on the grid. But the goal is that we want to avoid that because then, we're probably using fossil fuels to generate more power than is needed there. And presumably you'd instead prefer to just generate less fossil fuel power rather than curtailing renewable power. So those are some of the strategies that one can use.
Great, and there's three more. So this is from an anonymous attendee. You talked about minimization of costs as part of the optimizations. Could you comment on the risks of prolonging the use of fossil fuels within this approach, instead of, for instance, looking at the minimization of emissions within existing cost ranges?
Do you want to take this one, Simone, or should
I? You can start. Sorry, I was just reading it.
Sounds good. So yeah, so in an ideal world, if we were really trying to optimize power grids for emissions, for example, AC optimal power flow problem, instead of putting cost in the objective, minimize cost, we would put something like minimize emissions. In practice, unfortunately, this isn't how power grids are actually operated or how power markets are actually constructed. In some sense, the quickest way to get that to be reflected is if you have carbon pricing associated with power generation, then all of a sudden that gets internalized to cost, and now your optimization problem is reflecting that. But that doesn't fully necessarily solve the problem either. One thing that is kind of fortunate is that a lot of renewable energy or a lot of low carbon technologies, and particularly renewable energy technologies like solar and wind, what's called the marginal cost of producing power is zero, because the sun and the wind are free, whereas buying coal or buying natural gas to produce power is not free. So there are ways that luckily some aspects of cost do already align with various aspects of low carbon power, but that's not always true. And so that we have to do additional things to try to internalize that.
Great. There are some more questions coming in. I wanted to make sure that you're respectful of the speaker's time. So yeah, just wanted to check how many more questions I think you'll have time to answer.
I can probably stay for another 10 minutes if that works. Simone, if you have to drop off, you should feel free, obviously.
Yeah, I'll do 5 more and then I'll hop off if that's okay.
That's good.
Great. Thanks so much. So here's a question from Yvonne. What strategies can be used to gather realistic data from DER's behavior behind the meter? For instance, generation of electricity by solar panels before consumption.
So to start, so there are a couple of things there. One is there are actually some programs like Pecan Street, for example, that are actually trying to outfit small, like numbers of homes, but certain homes with very targeted metering infrastructure in order to then assess, what the DER behavior is and what the consumption behavior is and so forth. And in some sense, the hope is that by instrumenting, multiple houses, hopefully that are diverse and that are representative of different characteristics, that you can get a sense of what's happening. Now, in practice, there's a lot of selection bias in terms of which households actually participate and where these things are installed, but that is one approach in principle, getting targeted information on a smaller set of households in order to then extrapolate that more broadly. The other is that there are, existing entities that work very closely with consumers to do things like help make their demand more flexible, and these companies then get access to more targeted consumer data. They can't necessarily release it because of privacy issues, but there can be ways, if you're, for example, a researcher or company, to strike up bilateral agreements with those entities if you would like to maybe use that data, do research with them, commercialize with them or something else. Or again, there are some of these efforts to try to generate synthetic data based on this realistic data so that people can do studies even without those bilateral agreements.
I also think it depends on one's sensitivity to how accurate or realistic the data needs to be, and the balance between that and scale. So if you are, or if for your specific application, you're okay maybe with a smaller data set as a true reflection for that location, then I do 100% agree that interacting with stakeholders, maybe Beacon Street data might be like viable pathways. Now, if you are trying to get a sense of what it might be at scale, say for the US, you might have to sacrifice a little bit around what I'll call the accuracy of the data, depending on what you're trying to use it for a method that can help you do that at scale. Say, very simply, looking at just panel size, the latitude, declination, all of that to estimate output.
Great, thank you. There's just 2 more questions here. One from Harry. Where do you see opportunities for foundation models, i.e. pre-trained large models that can be reusable in power system analysis, besides weather prediction models that have already been done?
So Simone, I'll let you start because I think some of the work you do is actually more amenable to that than the work I do. And I'm happy to talk about why I'm skeptical, but maybe let's start with the more positive response.
Yeah, I mean, in principle, foundational models can help you, if well trained on the right data, can help you downstream with like fine tuning and not having to retrain. But specifically in like power and energy systems, we need to be careful. One around, do we already have in place the foundational models that are built on the right set of data to answer the questions that we have? So I'm not sure that there's a clear set of foundation models out there that can be readily applied in different aspects of power and energy systems, maybe in more so in like the remote sensing community than in other aspects. For example, I would say in operations and AC optimal power flow. I'm not sure that exists. So I think one would really need to be careful around what exactly we're trying to answer and where foundational models might play a role, maybe in like questions that have to do with like imagery, potentially language. But for other dimensions of power systems, I won't be as optimistic that it's there just yet, or even that it's the right thing, given the constraints that we have for grid operations.
Yeah, so I'd say something similar in that if you really think about what a machine learning model or a foundation model is trying to do, it's trying to, in some sense, figure out generally representative patterns that can be applied across different settings, maybe with some additional fine-tuning. And I think there are certain situations where that makes a lot of sense. So when you're analyzing satellite imagery, there's something common about kind of remote sensing data and image data that, there are some fundamental features in there that potentially are usable across different sets of applications. And so I can see places where foundation models would be helpful for tasks like, detecting solar panels from satellite imagery or detecting issues in power grid infrastructure using satellite imagery, because maybe there's something enough common among different satellite imagery related tasks that there's some shared features associated with that. Similarly, with things like electricity demand prediction, where electricity demand is driven by factors like behavior, where it's hard to write rules down for, but maybe there's some commonalities in those behaviors between different places. This is a place where machine learning, which is basically learning rules implicitly from data, maybe can be helpful in the idea that there maybe are common rules between these places. But when you're talking about actually optimizing the fundamental power grid, somehow it seems that the things that are common between different power grids are, in some sense, the underlying physical equations and constraints that we already know how to write down. And the things that then are difficult are the things that vary on top of those systems. So the fact that the parameters are slightly different between different power grids, and that's something where you wouldn't expect generalization to work very well. So I think in some sense, because here we have the ability to write down explicit rules that give that common grounding, whereas in other settings where we can't write down explicit rules, that's maybe where you want a foundation model. But here, yeah, I think we just know how to write down the rules that commonly bind different power grids, and we don't necessarily need to relearn them from data.
Great, thank you. And one last question from Team AI. Thanks so much to the speakers also for staying online. What are your thoughts around localizing customer energy data before requesting the data upon approval from each customer using edge and fog computing? I'm not really sure what fog computing refers to, but to boost their confidence in smart AI homes. We are working on home appliance energy saving technologies, but we need to build customer confidence.
Yeah, it's a good question. I don't have a ton of expertise in this particular area. But I guess upon reading that, I do think that there are uses of things like, right, like federated learning or decentralized storage of data or things like that to protect consumer data from being fully centralized or fully exposed to various places. But I think building consumers' confidence, I think it's really it involves really demonstrating to them that you are actually, right, preserving privacy. So just like sort of saying, oh, I'm storing it in a decentralized place. Well, is that decentralized place secure? What are the usage policies around that? If you're talking about sharing data up, can you provide any guarantees or certificates that you, when aggregating the data, didn't expose individual consumer data? So some of the considerations we talked about in the synthetic smart meter data generation and Faraday use case, for example, apply, where you can write down metrics, but you have to be able to demonstrate them to consumers as well. So I think this is a very reasonable and promising area, but of course, confidence needs to be earned. And so making sure that you're kind of doing that through customer engagement and by providing the right kinds of information and metrics is essential.
Yeah, exactly. Just to come back to the case study that you pointed out, I think the last case study, Priya, where one has to actually show metrics that demonstrate confidence and not necessarily contrive metrics. There's a balance there between like contriving metrics that show confidence versus metrics that actually show confidence. But I think one has to be quite thoughtful on what matters to consumers and reflecting that in the analysis of the system.
Great. I think that does it for all the questions. So thanks again, everyone, for coming to today's lecture, and also thanks to my support TA, Ruth. Yeah, with that, I think I'll just thank again the speakers, Priya and Simone, for an excellent lecture.
Thanks, everyone. Thanks for the great participation and questions and everything.
Thank you, everyone, and thanks to our TAs also.